Hello everyone, and welcome to the course Electricity and Electric Circuits. In this video, we want to introduce the series connection of resistors in an electric circuit. First of all, what is a series connection? As the name implies, in a series connection, all resistors are connected in series, one after another, as you can see on this picture. So basically, the resistors are connected like pearls on a string. And each resistor, or all resistors in the circuit, are subject to Ohm's law. Ohm's law states that the resistance is equal to the voltage drop, or voltage, across the resistor divided by the current that flows through the resistor. If you rearrange this equation, you can come up with different statements of Ohm's law. This one, for example, states that the voltage drop across a resistor, and when I say the voltage drop, I mean the voltage that you can measure across the resistor is equal to the current times the resistance. And then, if you want to measure or if you want to calculate the current of a resistor, you can divide the voltage drop across the resistor by the resistance. So, the main characteristic of a series connection is that the current that flows through all resistors connected in series is identical. That means that the current that flows through R1 is the same as the current flowing through R2 and all of the other resistors. And basically, what comes in terms of charge per time must come out. There are no charges created or destroyed within the series connection. Now, what do we want to do with the series connection? If we know the individual values for resistances, we can compute the total or the equivalent resistance in a series connection. And the total or the equivalent resistance is equal to the sum, let me write it down, R tot, which stands for total, or you could also write down Req for the equivalent resistance. That's equal to the sum of all individual resistances in the series connection. So that's the sum going from I is equal to 1 up to n. If you have n resistances in your series connection, you simply add up the individual resistances of the 5 resistors in the series connection. And in our case, since we have 5 resistors, R1, R2, R3, R4, R5, we simply add them up. We don't have the values yet. In the next video, we will be performing some calculations on the variables. So in a series connection, the total resistance is always the sum of all individual resistances. And in this regard, if you add more resistors in a series connection, your total resistance is gonna go up. Okay, the voltage drops across each resistor. I will label the voltage drops or the voltages as UI. The subscript I refers to each individual resistor. And the voltage drop, as I mentioned before, is basically the voltage that you can measure if you connect a voltmeter to the clamps of a resistor. So if I take R1, the resistor R1, and if I connect the voltmeter to the clamps of R1, so here and here, the voltage that the voltmeter will be showing is the voltage drop across that resistor. And the voltage drop can be computed by multiplying the current, which, as you know, is constant across each resistor, and the resistance of each resistor. the total voltage you can get if you add up all voltage drops of all resistances across the series connection. And the total voltage, therefore, will correspond to the voltage of the voltage source, or we call it the source voltage. So US or UTOT, depending on what you want to refer to, the total voltage is the sum of the voltage drops of all individual resistors, or across all individual resistors, and the formula to compute the voltage drop is stated here. And finally, the electric power dissipated by a resistor or by the whole system is P. P stands for power, and that's equal to the voltage, either the voltage drop across the individual resistor or the voltage of the whole system times the current. And that's the power dissipated by either the individual resistor or the whole system. And as I said, in the next video, we will be performing some specific calculations of these variables. As for now, I'm gonna say goodbye and see you soon.